Well, tensors. How would you get to the point where you can effectively talk about tensors? Because there's a lot of prerequisites with like with vector, when understanding vector spaces properly, understanding the underlying field. Like no need to do all the axiom stuff, but just the idea.
Okay, so just like to cover it quickly, I guess.
Yeah.
So fields, you've got like a system of numbers with addition and multiplication.
Does it have to be a system of numbers?
Well, it has to be a set.
Okay, yeah.
So I guess I'm calling a set. So I shouldn't say a system of numbers. I should say a set. And we like to think of fields as numbers with addition and multiplication, of course. I don't think I need to go over the axioms. Let's see. Like I'm trying to see what to cover and what not to.
Say like an example, maybe.
The most like common example is the real numbers as a field, because you can. I'm trying. What's an example of a field beyond like RD?
Oh, the complex numbers.
Right, but the complex numbers still kind of feel like R2.
Dual numbers.
Dual number. Are they? I think they are.
Well, addition and multiplication, yeah.
Addition, multiplication. The neutral element is 0, right? Inverse element.
You need canny.
Yeah. Can you? Yeah, addition's commutative. Is multiplication commutative? I think it is. Yeah, because it is. Because the only thing that's weird is like the squared thing. Multiplication
checks out for me.
Yeah, I think so. Cool. That's kind of interesting.
More examples. You could probably come up with some more messed up examples. Like I can give you one that's a ring, but not a field.
Yeah, rings are easier to think of because like there's things you can take out.
Well, yeah,
like
it's just
with multiplication,
the plus and the times is just less powerful.
That's the thing. Like the tricky thing with like finding a system that's a field for me, it's like you need to make sure that like the reciprocal is also still in there.
Well, the reciprocal for the I don't know if maybe inverse, because reciprocal
inverse is the right word, but like
different things.
Yeah,
because you were talking about addition, and I told you what's the reciprocal of +2. You know.
Yeah.
Like I guess -2, but it feels inverse is
weird. Okay. Anyway, that's it. And then vector spaces are sort of, a lot of the properties are the same except for multiplication, where instead of canny, you have a due. So there's two distributive laws, one with like vectors, one with scalars. Wait, I kind of forgot what the rest stands for. Associative. Okay, so multiplication has to be associative. Yeah. No, wait. Wait, what were they?
Yeah, it does have to be associative. Yes, that's correct. ADTV. Associative, distributive, backwards distributive, and then V for, I don't know.
I think it was U for unitary.
Oh, yes, sorry, U, not V.
Okay, yeah, so vector space is kind of similar. The interesting thing is that the tensor space is a vector space, and vectors are tensors. That's like something that kind of jumped out.
Whoa. What is a vector?
Huh?
What is a vector?
So a vector is an element of a vector space, but in some cases, vectors can be thought of as, I think it was 1-0 tensors or 0-1 tensors. I don't remember.
Well, the point is, if you have a vector space, let's say like a tensor space, right, which is an example of a vector space, then of course the tensor in that tensor space is going to be a vector. But I don't know. It feels weird.
Yeah, but the other thing is that.
But let's not talk about tensors. Okay, yeah. That's a little bit.
Yeah.
Next level.
I mean, I don't know what, like, we kind of. There's linearity, multilinearity is kind of.
Yes. Well, that's the whole point, right? Like you have a new, I guess, formally called category here, like a new a new level of thing. And then the next question naturally is always, what are the structure preserving maps between?
And that happens to be linear maps in the case of vectors.
Yeah.
Which is like linearity feels like distributive property kind of. I mean, it which it kind of is, but like it's specific in certain ways where.
Yeah. Well, it's all of the axioms. Like that's the point. Like structure preserving is that it preserves the axioms. So of course, distributive is one of the axioms. By the way, I'm just guessing here. Like I'm not 100% convinced about this.
Hold on. So let me just like think about this for a second. So what we're saying with linearity is that f of VW equals f of v. Wait a second.
What's f of VW?
No. It's f of v plus w. Whoops.
Okay, well, important question. What is f?
F is a linear map. And this is like what it means for a map to be linear. So f is a linear map.
From where to where? A linear map from where to where?
From v to v.
Okay.
Or it could be v to w. Let's say v to w. And if I say v to w, then this is the addition on v. And this is the addition on w. And it's kind of weird because I used v and w.
But that's only one of the parts of linearity. Okay.
Yeah. So that's one part of linearity. The other part is lambda f of v equals, well, I'm kind of writing this the other way around actually, but yeah. So this is the S multiplication on v, and this is the S multiplication on w.
Okay.
And that's just linearity. Yeah.
Then what's the big picture here? You have vector spaces, and then you have structure preserving maps on these vector spaces. What's the point of having structure preserving maps? Is it to classify the vector space? Because that's what we did with topology. So we talked about just the topological structure of XO, and then we talked about structures preserving maps, aka maps that are continuous, whatever that means, which in this case is the preimage of open sets are open. And then we used this definition of continuity to classify the category of topologies into connected and not connected, into compact and not compact. But it's weird because are we doing the same thing here with vector spaces? Are we going to use this definition of linearity and then classify vector spaces?
What do we do? Because I feel like we use linearity.
That's the crazy part to me. We don't.
Right. We just because I mean we've seen linearity being used. So like I guess like saying what is it used for? It's just to use. It's just so that we can like talk about like convert. There's a lot of things we use linearity for, but it's not to like classify vector spaces in a sense.
Well, maybe for fun. Has there been a time where we have classified vector spaces into vector spaces with a particular property? Maybe, I guess, dimension? No.
I was thinking dimension too.
But you can have, but first of all, dimension depends like on basis.
Yes. But basis.
But not
okay,
even
maybe that's it. Because like basis is based on linearity.
From different dimensions. That is structure preserving, I think.
Because I'm thinking like, do we need linearity? Because so we need bases for dimension. Do we need linearity for bases to talk about bases?
Oh,
we need linearity to talk about change of bases, right? But just bases.
I'm not sure. Here, I'm just searching up really quick. Vector space classification. Like, do we classify vector spaces? This is weird because I feel that's the whole.
Because like what makes the vector space of R2 different from the vector space of cubic polynomials or whatever.
No, it's more like, are they a part of the same classification? Is there a structure preserving map between the two? Wait a second. So let's say we're talking about topology. And so in topology, you come up with continuity. And then from continuity, you start asking these questions. Oh, my board is not working.
Okay. In set theory, use isomorphisms to distinguish one set from another.
Yeah. That's like the base version, like to classify sets. Actually,
in topology, we use it to distinguish topologies from another.
I'm not even sure if we've classified sets. Well,
yeah, I don't think it's about classification. It's about just like telling them apart in a sense.
Because the classic example, let's say you have a donut and a ball. Those two are different because there does not exist a structure preserving map between the two.
Yeah, you cannot which in this case, you cannot continuously deform one into the other.
That's right. Now for sets, the natural numbers and some finite set, like 1, 2, 3, are also a part of a different category, finite and not finite, because it's impossible to have an isomorphism between them.
Mm-hmm. But it's also just like this, right? Like if you have, that's bad. If you have a set 1, 2, 3, that's not isomorphic to the set 7, 8, 9, 10.
Are you sure about that? Yes, you're right. They have different cardinality.
But it would be isomorphic to 7, 8, 9.
Yes. Yeah. Okay, so I don't know if you've heard of this word, but cardinality, which stands for like the number of sets in an element, right? So you have like a set of cardinality 2, but then you also have a set of cardinality infinite, like the natural numbers, right?
Yeah, okay.
So that's that. So we actually do classify just sets using this.
So we use this to classify sets based on cardinality. We use topologies, isomorphisms to just distinguish between topologies. It's almost like, I think we usually say when like two things are isomorphic, you can treat them as the same thing. That's sort of what we do, isn't it?
Isomorphic means just that there exists a map between the sets. Am I correct? But then
yeah.
Homomorphic is when there exists a structure preserving map between the two. Or homomorphic might be for just topologies.
So topology, I think, was like homeomorphic. And then homomorphic was
just the general case.
Yeah, I don't remember. With sets, it's like there exists a bijection between the two sets.
Oh shit, you're right. So yeah, isomorphism is very general case. But wait, what is homomorphism then? It's also a general case.
What was a homomorphism? I keep forgetting. Oh, homomorphism is just like a structure preserving map, isn't it?
Yeah.
And then homeomorphism is the homomorphism for topologies, kind of.
That's right. A homomorphism is an isomorphism if and only if it is bijective. Oh, you're right. So homomorphism is to refer to the actual mapping object. That's why you say there exists a homomorphism.
Okay.
And then you say two things, but then what is an isomorphism? Oh, if it's bijective, I see.
Wait, what's the difference between an isomorphism and a homomorphism? What?
Yeah, homomorphism is the object name of going one way. Isomorphism is a homomorphism that goes both ways.
Wait, hold on. I just searched this up. A homomorphism is a structure preserving map.
Yeah.
And the isomorphism is a structure preserving map whose inverse is also structure preserving.
That's right. So homomorphism could possibly go only one way. Cool.
So
Okay, anyways.
homomorphisms can lose information. Yeah, anyway.
Yeah, exactly. Yeah, homomorphisms. Okay, anyways. But then, okay, yeah, back to the idea here of sets, or sorry, of vector spaces where this doesn't happen. I think it maybe does. We have to think more. Like, I'm sure people do classify vector spaces. But do they?
I don't know though. But the thing is, like, linear maps are used for a lot of things, I guess. So you can't just like say are they necessarily used for...
But see, this is the weird thing. Like, I've thought about this, and it's like there's a whole additional level. So for topology, you look at X, this, Y, this, and then you ask the question, is there a homomorphism or even an isomorphism between the two? And then that means that one is deformable into the other, whatever that intuition means. But you don't actually look at the object F that maps between one and the other. Like you don't actually care about the map, like what the map does. You just say if there exists a map, then that's all we really care about. But then for vector spaces,
you would do like look at.
Of course, yeah, you actually look at this mapping object F.
Because it's actually like a useful thing.
Yeah, and then this is a vector space in itself when equipped with the right addition and multiplication, which is something that never happens here.
Yeah, like the maps aren't sets. Or are
well, of course, yeah, the maps are sets, but the point is that they're not self-structuring, referential, whatever.
Yeah, I don't know. Like there's no like vector spaceception or whatever, like setception or whatever. Like
yes, well, or for topology, there's no like you can't look at this map F and equip it with it. I mean, maybe you can, but that's like probably a whole different area.
That's a weird thing, actually.
Whereas for vector spaces, this is the whole point. The whole point with tensors is to look at this. It's like, I'm not sure if you remember this discussion we had a while ago, but with Hom. So Hom is like an official term to mean look at all of the so the set of homomorphisms between a set X and a set Y. Or, well, what am I saying? So let's say X is a set and Y is a set. So just a set structure.
Then Hom is the set.
XY is the set of all possible Fs.
Yeah. And in the case of vector spaces, we do the same thing.
Set of all possible linear maps, correct? Yeah.
Yeah.
But then you can also do Hom for topology, right? But that's kind of meaningless because in topology, we don't explore that fact. Okay.
Or at least, or maybe we do, but like, at least for our purposes, we don't need to.
In topology? Well, no, I kind of looked into this. They don't really do that.
Okay.
Unless I didn't look deep enough. But anyways, okay. So then, okay, the point is we're talking about all of this to understand vector spaces. And then
tensors. Ultimately tensors. I think one like special term that I keep forgetting, but like it's really useful to remember is the endomorphisms, which is
that's just Hom VV.
Yeah, so the set of all linear maps from V to themselves, which.
But as Schuler mentioned, like the entire point is you're supposed to become very used to Hom VW, and then all of the other things are just special cases of Hom VW. Like the dual space is just a special case, Hom VK.
Yeah.
And then the endomorphisms are just a special case, Hom VV. So maybe it's worth it to act like maybe this is the point. The point is you're supposed to become used, like, let's say we're explaining this to somebody. Maybe it does make sense to become used to the general theory first and then apply it specifically.
Yeah.
So what is the general case here?
The general case is just, the general case is the set of linear maps from V to W.
So it's the set of maps F from V to W. I would end it here, but that's a lie because you actually need to add the extra condition
of linearity.
F is linear. So what does this mean? F is linear. It means,
well, we wrote down earlier.
Yeah. So it means that if you add another V or scale it up by some factor, lambda, then you get the resulting structure
Alternate scale, yeah.
W. But what does it mean here for it to be like y is linear? Oh, I think we already asked this question before and we kind of dead ended. But yeah, why linearity is structure preserving?
Yeah, like why do we look at this linearity thing?
Shit. But we looked into this and it was a dead end. Or maybe we didn't.
Or we didn't like get to where I guess we didn't get to the answer.
Yeah, maybe we can ask Praveen. He might know. Okay, anyways. So yeah, so this is the idea of Hom VW. It's literally like you have the structure V, the structure W, and then very weird to do because we've never done this before, but you look at the set of all maps, and then it's kind of like a pyramid of it. Like 1, 2, and then you look at the set of all maps. But then you can pair it up with the set of all other maps, or you can pair it up with itself and it goes one level higher.
Yeah, you can do like the Hom of the Hom, like
yes,
it's kind of crazy.
And then that's where all of the interesting phenomenon emerge, because this is the general case.
Yeah.
Then what are tensors? Like I know we're kind of skipping ahead here, but tensors are just.
I mean, I think tensors are kind of the next logical step.
Are they?
What else do you need to know before tensors? Covectors are just an extension of Hom.
Sure.
Right, but they're just an extension of Hom, which is in this case, instead of W, we have K, which is the field.
Okay.
And oftentimes oftentimes K will end up being a real number or a complex number. Or this set of real numbers or complex numbers.
Yeah. Like 100% of the time. But I'm trying to understand the relationship here. So you have V and W, and then you have Hom VW. But the point is, most of the time you don't actually have a W, you just have V. And then you can look at Hom VV.
I mean, sometimes you do have, yeah.
And then once you have Hom VR, then you can do Hom VR or Hom of a Hom VR R to get the dual vectors, like these guys.
This is an interesting thing because I think like there's the case where like this thing is isomorphic or the same as V.
Yes.
If it's finite dimensional or whatever.
Yes,
so that's like a whole can of worms.
I know, right? Maybe this is the best way to see it. So let's say you start off with your original V, your beautiful little V. You can go one direction upwards and look at Hom VV. You can also go one direction sideways and go Hom VR. But then you can also take your Hom VRs and go Hom VR R.
Whoa. Which would be, okay, hold on. Now let's think about this.
This is V star.
If we think of V, this is going to be witchcrafty, what I'm thinking.
Let's see.
Let's see. So if we think of them as row vectors, and this as column vectors, right? Because when you multiply these two, you get a real number. What would this object be? This would be an object where...
Wait, which one? Which one?
What would this object be?
Oh, row vectors, or sorry, column vectors again.
It's a map from... right. Yeah, because it's a map from... Oh, yeah, because it's a map from the row vectors to R. So yeah, it has to be... You can multiply column vectors here as well. Which is kind of interesting. And again, this is only the case for finite dimension, which is usually implied by the row and column vectors. Or not always, actually, but yeah.
This is just such a weird structure. And the point is that for finite dimension, you have an association like this. And then if you choose a basis, you actually also have an association like this for finite dimension. So messed up.
Yeah.
Okay, anyway, let's just move ahead and maybe be cavalier, even though we don't fully understand what's going on.
So I think like to me, the next two options to talk about are either Hamel-bases or like tensors right away.
Well, dual vectors first.
Well, right? Dual vectors are the covectors, right?
But are there properties we need to talk about? I mean, I guess one thing is
There's like the dual
we probably
space.
should have mentioned that for Hom VW, there's a plus and a times. This is probably one thing we should have mentioned.
Yeah, but
That's inherited, right? But who cares?
It's like point wise.
It's always enough. Yeah. So yeah, I guess we've talked about vectors and covectors. Now the next step is to look at tensors. Or do we talk about bases first?
We can talk about bases quickly, I guess, because.
But what's the point of talking about bases? To talk about dimension. Why do we need dimension? Shit, it's because, yeah, that is needed to talk about the V star isomorphic to V.
Right.
Maybe this is what we need to focus on. Why this over here? Let's just do that. So yeah, let's first talk about bases.
Well, the proof is in like the lecture notes. It's kind of like weird to follow. Yeah, it's kind of weird, but okay, we can like try to like go through it, but I don't know.
Let's do Hamel basis.
Okay, so we start with Hamel basis?
Yep.
Okay, so a Hamel basis, and I believe like it's some kind of B, like that's the letter they use, which is a subset of V, which means it's a collection of vectors, and it's not necessarily a finite collection.
Mm-hmm.
But the conditions are that even if it's like, no matter whether it's finite or infinite, it has to satisfy the condition that any finite subset you take, and because it's finite, you can number them B1 to Bn. For any of these, you have to be able to say that they are linearly independent, which means
We don't need to go into, well, yeah, we know linearly independent and also that they span the vector space.
Yeah. No. So the collection has to be linearly independent. And the whole thing has to span V.
Yeah.
Which means that any vector can be expressed as a linear combo of basis vectors. Cool.
How about we give an example of a basis for R2 or something?
Yeah, we can do R2, and my basis vectors can be the tuple 4, 3.
What? Why about just 1, 0? Let's go simple.
I want to like test my limits by like doing weird tuples.
Let's do it.
So 4, 3, and okay, so they can't lie on the same line. So just any other like 1, 2, that works. And then are they linearly independent?
So yeah, well, okay, in this case, we haven't actually talked about decomposing vectors into its components. So the only reason you've introduced a basis here is to calculate the dimension of R2. That's it.
Yeah.
Okay.
But in this case, like I kind of like use the idea that I already know what R2's dimension is, because I only like said, yeah, I'm going to choose 2 basis vectors. I kind of said that right away.
Imagine that computationally you tried out all of the variations with just 1.
Yeah, like you have to like think about that.
And then you tried all the combinations for 2 and you're like, okay, this one works. Good, we move with it.
Yeah. So this is linearly independent, and we know that because you can't like multiply each of these by something to get this. So if instead of 1, 2, I had chosen not 6.
I don't know if that's the definition of linear independence.
It is.
It's just that you can't reach 0.
Oh, right. That's true. So for example, because like if I instead of 1, 2 had chosen 6, 8, the reason not 6, 8. Why do I keep saying that? 8, 6.
Or wait, no. It's you can only reach 0 if all of the component.
Yeah, exactly. So in this case, I can reach 0 because
you can do.
What I can do is
-1.
Multiply this by -1/2, and then if you take that and then you add them, you get the 0 vector.
Which is bad, yeah. So that's linear.
Whereas you can't do that for 1, 2.
But then the next question is, does it span the whole vector space? So can any V be expressed as a combination of these guys?
And so the answer just is yes. like I don't know how to I don't really know how you're supposed to prove it. I guess I can just like say like, you know, I can say like if you give me any element of R2, I can do it. Like if you give me like 7, 9,
You can do it, yeah.
I could do it. Now I'm thinking like, how would I do it? That would be kind of annoying. But yeah,
Wait,
how would you?
this? You can put these for abstract variables. XY is equal to I don't know, alpha.
Oh yeah, wait, how do you do this?
Times 4, 3 plus beta times 1, 2. All right, you're done.
Oh wait. Okay, hold on. So I guess like if I actually wanted to solve this,
you will literally just say x is equal to alpha 4 plus beta 1. So now any x's can be reached.
Yeah.
And y, like I don't know, like it's a lot of variables.
If I want to do this specific case, it would be like 7 is equal to alpha 4.
Yeah,
plus
exactly.
beta.
Yeah.
And I would solve that system.
Yeah.
And then it would be like 9 is equal to alpha 3 plus beta 2. Yeah, and I would just solve that linear system. Cool.
Okay.
And I guess we should also talk about change of bases. Change of basis.
That comes later, in my opinion.
Yeah, it kind of does. Yeah. Should we try to talk about how V star is isomorphic to V?
I want to do that, but first, maybe it's worth talking about tensors.
Yeah, that's kind of like the whole point.
Today. No, what I'm saying, like for order, it makes sense for me to talk about tensors than to talk about the isomorphism.
Okay. I think like some things about tensors kind of clicked for me that didn't click before.
Okay.
Today.
Let's see. So what is a tensor? Well, shit. See, this is the bad thing. Tensor is kind of closest to vector, where you can't say what is a tensor or what is a vector. It's just an element of a tensor space. That's it. So well, what is a tensor space? Like you have to define addition and multiplication to make sure that the tensor behaves correctly with other tensors, or else it's not a tensor.
I'm not sure about that though, because I think in this case you can say that a tensor on V is a multilinear map. So you don't need to necessarily. I don't think you don't need to, because like with V, they're only defined based on the axioms of vector spaces. But I don't know if T is defined on the axiom of tensor space. Like it's not exactly the same thing.
The point is, it's not a linear map. It's actually an element of a space of linear maps that have some sort of addition and multiplication or scalar multiplication defined. Like, yes, it is, I guess, a multilinear map, but it's actually just an element of a multilinear map space with addition and multiplication defined so that the tensor behaves correctly with other tensors.
Yeah.
And that's the key part. That's like saying a vector is, I don't know, you could give something, but then I would come back with, a vector is a vector space or is an element of a vector space that behaves correctly with other vectors.
Right. So if you don't talk about the whole space, you can't talk about how it interacts with
other tensors.
Other people of its kind.
Yeah. So it's like a tensor is a part of a tensor space, a tensor is a multilinear map that behaves correctly with other multilinear maps that are a part of the same space as it. That would be the full thing.
But the thing is, like when we start like trying to, I guess, like explain tensors, with vector spaces, the first thing we do is write down the axioms of vector spaces.
Yep.
But with tensors, I think we start, like, even though like when we talk about them, we start with the whole a tensor is a multilinear map thing.
Do we? Is there a way to talk about tensors using Hom?
That might be the Hom tensor.
No, there's not. Crap. You might be right.
That might be what the Hom tensor joint is. But we don't fully get that.
Give your explanation of tensors. Let's see where it goes.
Okay, yeah. So let's start with this, I guess. So a tensor, a PQ tensor over V on V is a multilinear map. So we'll say it takes in Oh god, that looks horrible.
Oh, I think I see what you mean, because you're right. Tensor, yeah.
Yeah. Okay. The point is like, hold on. Let's do that, and then Cartesian product V, V. Okay, and then there's
the map into R.
There's P of these guys, Q of these guys, and yeah, it maps into R or K.
Yeah. Okay. Yeah.
That's kind of crammed, and we write TPQ on V as, and now this is like a tensor product, and it's just a symbol.
No, that's just a symbol. That's not the way it's actually defined.
Yeah, it's just a symbol. It's not like what the actual tensor product is. So here we write PVs and then QV stars, which again, but this doesn't really necessarily matter because it's just a symbol.
It's actually defined as the set of all T, such that what? Is that it? Just such that T is linear or something?
Such that T is a PQ tensor on V.
Oh, yeah.
Oh, so this is the tensor space.
Yeah. So it's actually not defined tensor space first, then tensor. It's actually defined tensor. Yeah.
So it is actually defined that way, tensor and then tensor, because you can't say T is a PQ tensor over V without saying what a PQ tensor is.
Yeah, which is this.
Which is kind of weird. But yeah, so with that.
Well, okay, well, one important condition is that it has to be multilinear.
Yeah, multilinear. It's a multilinear map, right?
Yeah, which means that it is bilinear with each component or something.
It's linear in each component. So
yeah.
Which.
Well, what does that mean though? Because that's different than normal linearity.
I think it's like it's linear and bilinear and trilinear and all of these things at the same time.
Well, yeah, because it goes all the way up to.
Yeah. Now actually,
but it's not linear. It's not linear.
It's not linear.
Bilinear. It's only like bi stands for 2, tri stands for 3. It's only x linear. So
yeah. That's
because think about it. If you have a tensor like this, and you said it was linear, then it would have to. I guess maybe it is linear. Shit, man.
It's gotta be. It has to be linear, right? Because
no. I doubt it's linear. I think it's a special case of non-linearity.
Maybe we can like think of examples. So like
here, I have a very simple one. Plus VV returns V. This isn't a tensor, but this is just to discuss bilinear and linear.
Okay.
So I would argue that this addition is, let's make it even simpler. Let's say R. I would argue this is bilinear, but not linear. Okay, how do I prove that it's not linear? Take a look. Imagine you have, so this is a tuple, right?
What? So why are you calling it plus though? Because that's kind of weird.
It doesn't matter. The point is we're talking about bilinearity here. And linearity. I don't actually care about vector spaces here. Like forget about our whole discussion about vectors. We're trying to focus on bilinear and linear. So let's just talk about some random function here. So this is a tuple. For it to be linear, you need to have AB plus CD.
No.
You can
if you write it like that,
you can do
then
both.
This would be R2.
Wait, why R2?
Because this means that, like, just like this, it means that it eats 2 real numbers, not 2 tuples.
Oh. I see what I did wrong. One sec. Plus AB. No, shit, man. What the hell does linear mean?
I think so. Addition is linear, right? Just like regular addition of like real numbers, because No, because a linear also implies
Requires
multiplication.
scalar multiplication.
That's the weird part. Okay, I know what to do.
Okay.
So let's say F is a linear map from R to R, right?
Okay.
Which takes in a number X and spits out 4X plus 3. Now the question is F linear?
No.
It's not?
No, that's not the point. The point is we can't talk about bilinear here. How about this? Because bilinear needs two things at the top here. So you can talk about linear and bilinear. I don't know. Here. I slight modification on your example. F is a map from R cross R to R.
So that would take in, let's say, X and Y. And what would it spit out?
Just do X plus Y.
What does bilinear mean?
So linear would mean that if you have F of, if you have F, oh, come on.
Okay, wait, I think it would mean F of P Q. Aha. What? Can you talk about linearity?
There you go. I got it. In this case, I think you can, yeah. F of lambda A B C T. No. What a mess.
Hold on, we need to get this straight.
F of lambda A.
Okay, I think the tricky thing is like we're talking about like just R. We need to like talk about vector spaces. Like a little bit more complex vector spaces. So like maybe R2. I think R2 is like an easier way to think of it.
No. Look. This is good, right? There definitely is a case. What the hell is linearity? This is bothering me. Oh my God. Something is linear if do you have it written down somewhere?
Yeah. So if F, because it's like if F of V plus W is, if F of V plus W is F of V plus F of W. So let's start with that.
Okay, yeah.
Let's start with just addition. It's like the addition thing. So without the lambdas. Now the issue with this is that
but here we can easily add the lambda right here. Boom.
Yeah.
Okay, so let's try this. Is this linear?
Now the issue is like this implies that you're only entering one parameter into the function, but here we're entering two.
So we need to pick a V and a W, or Jesus Christ.
Wait, hold on. Let me like rethink of this for a second.
Oh, here, boom! I got it.
Wait, sorry, one second.
Shit, no! Oh my God! It takes only one parameter.
Okay, it's bilinear if so bilinearity. So bilinearity is when you have two components. You can't talk about linearity with one component. You can't talk about linearity with two components.
Actually, I think you can.
Oh.
But the point is that the two components have to scale the same way.
Okay, there's an example, right? Like, so if we have a map.
Wait, look, Avnish. I think I figured it out. Avnish.
Mm-hmm.
Imagine this as a single argument. Then it goes from 1 to 1.
So you mean like a tuple?
Yes.
Okay.
So this is actually f. It only takes in like a tuple.
Oh, that makes sense. Oh, right, yeah. And then
That's how you can talk about
x plus
linearity.
y, right? Which is a single number. Right? And this is linear because if you have f of...
Okay, here you go.
No. Wait, hold on. Wait, erase that.
Erase is y.
Hold on, I want to try something. Because it's not quite that. It's like... Okay, yeah. But what linear means, like the reason this is linear is because if you have... Hold on. If you have f of lambda... The reason this is linear, so for that I need like two things. You would need like a
Oh my
b
god, I see what you mean.
plus cd. So
And
this
then,
is no, this works, right? That becomes this needs to be, I think it's a lambda of f of ab
you're right.
plus f of...
Well, let's give it a
tuple
try.
CD.
So here we'll have, this is the first side and then this is the second side.
Wait, can we just clear?
Let's do it.
No, just like clear the whole screen.
Well, except for the top right there, that one's useful. We finally wrote it down. Now we're checking
right.
the linearity.
So let's say we have...
You'll just write down the right side and write down the left side.
So should we like plug something in like the tuple 3, 5?
No. This is fine. Look. Make sure both sides are equal. So actually evaluate.
Oh, actually evaluate that. All right. So this would become... That would become f of... Hold on. Let me choose a different color. F of lambda a lambda b plus d. Yes.
Can you evaluate the rest of that? I'll evaluate the other side here.
Wait. Because wait, no. Because hold on, I'm confused. Yeah, let plus lambda b plus d. Exact. Okay.
Fuck, they are equal. So this map is linear?
Yeah, this is linear.
I don't believe that though, because it's also bilinear.
No, it's not bilinear.
You sure?
Yeah.
Oh, you're right. It's not bilinear. Holy shit, you're right.
Why is it not bilinear though? I need to think.
Because A times B would be bilinear.
Yeah, a times, but like, why is this not bilinear? Like,
Yeah,
what's the difference with bilinear?
We have to test it, but I suspect it's not bilinear.
Because like in the notes, like the notes say that this map is not bilinear because like the notes give this as an example.
Yeah. Because of course, so bilinearity is a special case of non-linearity. It's a special case where all of the parameters and the tuple happen to do some special shit together. But as a whole, if you pretend the tuple as a whole is like a black box, then it's not linear if something is bilinear.
Yeah.
Here, do you want to do a 2 for 1? Here, we'll split the board in half. You prove that the one we just did, f is defined as x plus y. You prove that this is not bilinear, and then I'll prove that f xy is equal to x times y is linear. No shit, is
Bilinear.
not linear.
Right. Okay.
Oh, here, do you want to do a quick matrix? Look at this. Okay, linear. Bilinear?
Wait, what?
Well, what am I trying to do? Wait, linear, bilinear. So wait. X plus Y,
XY.
is that it?
I don't know.
Oh, wait, and then not bilinear. Not linear. No, that doesn't make sense.
Wait, this yeah.
Okay, the point is that X plus Y is,
Linear but not bilinear.
and then XY.
And let me think of why. So the reason is because, so for it to be bilinear,
it means the scale.
for it to be bilinear, f of
Oh, I think you need this.
I think it needs to be like f of lambda a plus b y
Yeah. And the other
is
way
equal to lambda of whatever that space.
Wait, no, Y0 has to be Y0. Like, has to be like held constant.
Yeah. So I'll just do that. Is equal to lambda f of a y0 plus f of b y0.
Let's give it a try. And we don't, like, in theory, you should also prove the other way around as well, like with Y being variable. But both of our equations are mirrored, like if you replace X with Y. So we only need
to. I have to prove I would theoretically have to prove the other way around, right?
But our equations are mirrored, so we don't actually have to.
Yeah. So if I do this, so let's evaluate this. F of lambda a plus b y0 would be, so ls would become so what it actually is f of lambda a plus b y0 is actually lambda a plus b plus y0 ls, and then rs.
Okay, for me, it checks out. This map is in fact bilinear.
Okay, I think I'm almost there. 1 second. So that would become lambda a plus y0 plus b plus y0, which would become lambda a plus lambda y0 plus b plus y0.
Which does not check out.
Right, and that's interesting because just because of this factor. Anyway, wait, so let me explain that again. So in red, we have the condition that it needs to satisfy to be bilinear. So if we simplify the left side, you add the left and right. So lambda a plus b is the left, and then you add that to y0, and you're just adding them. Okay. Whereas with the right side, you have this, right? So you add the a plus y0, and then you get a plus y0 right here, and then you multiply the result of that by lambda, so that distributes out. And then here you just have a b plus y0, which becomes that. So yeah, basically, because this is not equal to this, that's the reason it's not bilinear.
So this here is linear, not bilinear.
Yeah, and we've already proved that it's linear. And now let me look.
Bilinear.
Okay, wait. Now can you talk through yours? I guess.
Huh?
or hold on, I just want to like look at your proof again.
Okay. Yeah, I can explain it. So, I mean, it's simple enough. You just check the condition and then they're equal.
Okay, so this is the condition, right?
Yeah.
This is the condition for it to be bilinear. But if you actually evaluate it, you get, okay, you multiply. So lambda AY0, BY0. And here, AY0 lambda plus BY0. So they're the same, which is proves that it is bilinear. Okay, but now it's proved that it's not linear.
Yeah, sure.
Actually, let me just clear my part as well.
Well, I think we can do it on just this side. I mean, it doesn't really matter. Here, let's see. So condition for linearity is am I correct?
Yeah.
Here, let's evaluate both sides.
Wait. Oh, yeah. Yeah, lambda A plus C.
Which they're not.
Right. Oh, okay, that helps. That makes sense.
Okay, cool.
It still doesn't feel like fully internalized though. Like you have to like walk through these proofs to check linear versus bilinear.
Yeah. I think the point is that bilinear or bilinearity is a special case of something being nonlinear. Right? So you have linear and nonlinear. And out of the nonlinear, you have a special case of a bilinear.
Yeah. It's kind of tricky, but yeah.
No, literally. So if we organize this in a big square, this is all maps. You have linear maps and nonlinear maps. And then out of the nonlinear maps, you can divide an extra time into bilinear. And then just not anything.
But there's also like trilinear, right? Like trilinear is also a thing.
That'd be an extra case over here.
Of the not anythings. So it just kind of like keeps
trilinear and then quadrilinear. What's the name of this again? The golden ratio or something?
The golden ratio, yeah. Well, this is like the golden spiral, something like that. Yeah.
Interesting, huh?
Well, actually, it's not necessarily. Okay, yeah. That's kind of cool.
Good.
But anyway.
Okay.
So with that, tensor multilinear maps. Yeah. Oh boy.
Let's see. So yeah, we have our definition of tensors. What's next? So the whole point of talking about that is to say that multilinear means that it is not linear. It is bilinear, but like extra fucking bilinear. I don't even know, man. Mind mess.
Yeah. It just doesn't feel, I feel like I haven't internalized bilinear. Like I can see a map and like instantly tell like, oh yeah, that's linear, but not like if it's bilinear.
So bilinear is like if you have a map that takes X, Y.
It's like if you keep one slot fixed.
Yes. So if you were to do G of X to Z, because you literally like put in for any Y.
So you like you keep the Y slot fixed. Then the G of X to Z has to be linear. Okay, yeah, yeah.
And for all x, h, y to z.
So it like goes both ways.
Yeah, which is why x times y goes so nicely, because when one of these you choose something like y0, you're left with just x, which is linear.
Oh, that's true.
And when you do x0,
Identity is definitely linear.
Like, yeah, x0 times y, this is linear for just y. So,
oh, that works. That works.
All right, boom, fucking bilinearity understood.
Let's go. And then if you for trilinearity, that's the same thing. Like you keep 2 slots fixed, then you check if the third slot.
You're left with the linear map.
Yeah.
Okay, let's see. Let's talk about tensors again. So you have a tensor space T
PQ on V.
V. And then you can define addition and multiplication or scalar multiplication. And then this becomes a vector space in its own right, where each tensor can add and do stuff on its own. And then the crazy part is that this vector space must have a basis, but the basis can be explained as a combination of the earlier bases in terms of tensor products. I don't even know.
Wait, let's go to bases later. I think first the tensor product, right? Yeah.
Do you think so? Maybe can we skip it? Is there a way to skip it?
I don't think we should.
Maybe we go right into examples. So we say, whatever this Greek letter is, do you know the name?
Phi?
Phi?
Is that phi? I think it's phi.
Call it phi. Let's hope it's phi.
I'm pretty sure it's phi, yeah.
So let's say phi is a map from V star cross V to R. And let's give it an actual property here. So first of all, we say V is R2 with the standard like multiplication and addition. And let's say we pick a basis for V.
1, 0, 0, 1. Also, did we talk about duals, the basis?
Yeah, we did. Yeah, we talked about basis.
Okay.
Since it's R2, actually, it's just going to be 2 of these. Then there's going to be V star, and V star will have basis F1, F2. Maybe before even talking about this, one important fact to mention is that you can decompose any V into VI, EI. Like this is crucial to me right here. This is like the whole point of vector spaces is the fact that you can decompose it into your nice vectors where VI is going to be one of these.
Yeah.
Right?
Where VI is just like from the set of numbers, like from the set of like from the field. VI is an element of the field, basically.
Sure, but the point is you can organize the VI.
Yeah, you can organize them like, yeah, you can just like think of, yeah, you can think of it as like, yeah, like just think of the vector as its components.
If this is a covector, you can also do WI, FI, where this is thought of as a row. But then here's the crucial part. If you have a map phi or psi or whatever this Greek letter is. Wait, so I think this is psi.
Yeah, that's psi.
Okay. So if you have phi, you can decompose phi into its components.
And this is where matrices.
And then you can organize this as a matrix.
Yeah.
The crucial part is what happens with this here. Like this is, it's like you make your own custom base vectors for, so this is an element of the tensor space T11V, right? Which is going to have its own bases, like it's totally separate thing. It's going to have its own basis vectors. And those basis vectors, there are going to be 4 of them because there were 2 of these. And the 4 of them are going to be, all right, basis vector 1 is going to be E1, F1. Basis vector 2 is going to be E1, F2. Basis vector 3 is going to be E2, F1, E2, F2. And then the tensor product is defined for specific tensors. So this is perfectly fine here.
Right. And what would the tensor product be here?
Huh?
In this case, what would like, in this case, what would it look like?
You'd have to give E1 and F1, or the E's and the F's actual values here. So E1 would be like 1, 0.
Yeah, so if I did that, then like, how would it look like?
Then what would happen is that your tensor product, E1, tensor product, sorry, the one is actually at the bottom. E1, F1, let's say E1 is 1, 0. And
or row. Well, that would be, E1 would be E1 would be a column. Oh, okay, yeah.
I'm just saying like as they are vectors, like actually as what they
like
are
this.
defined as, yeah.
Like as tuples.
Let's say A. Then this here would be defined as a 1, 1 tensor. So this is an element of T1, 1V, right? But it would actually be solidly like down to the ground defined as, it would be, E1, F1 takes in a covector and a vector because it's a 1, 1 tensor, and it spits out a real number.
A covector and a vector. So W is the covector, V is the vector. So W will hold on, let me think about that. Wouldn't it be E1 acting on W?
E1 is a vector. This is a covector. This brings a vector into the underlying field.
Right. Hold on, give me 1 second.
Yeah. You know what's a maybe smart thing to do? You know how earlier we said we can decompose a W into VI, FI? Maybe we do that here.
So we say, we should do that. So W would be
VI, FI applied to E1 times F1 applied to VI, EI. And because of the way that...
Wait a second, but I think there was like one case in the lecture where you end up seeing a vector act on a covector instead of the other way around.
But I think the point is what actually happens is the covector acts on the vector. Because this is a vector can act
it's
on
like the same thing.
It's part of V star star. Then
so we leverage that.
But the point is we don't actually have to talk about that here. Because V star star is only attached to V if it's like whatever basis shit, whatever the basis is finite. But okay, well the question is what happens here.
Well, we can decompose the E1 as well as like
one. Okay, well, these are just scalars, right?
Right.
They can go to the front. Like you can just pull it out. And then you're left with shit. E1 is a 1, 0 tensor. So it's going to bring Fi into F1. All right, shit.
I think so.
Then F1 takes an EI into E1. Like just by definition, that's literally what it does. Like for some random EI. Take it to E1. Shit, what does this mean though?
Why am I so confused? Like, wait, hold on. I feel like it's on the tip of my tongue. Like,
Yeah.
okay, hold on. Can we go to the next screen? I just want to like rewrite the definition of a tensor product.
Yeah.
So, and see if this helps. So, a tensor product of two tensors, T and S, which
Quick
are
question. If I do this, does it bring you back?
Yes.
Shit. Okay.
Wait.
So
what's the problem with that?
I just
you want to do something at the same time?
need to see this. Yeah.
Okay. Well, I can try to write it out quickly, I guess.
Okay.
So this is elements.
Wait, how about you write it down here?
Oh, I don't know if I can fit it.
Okay. Shit. Wait, remember the point is that we have a map phi here.
Okay, well, quickly, I guess it's like T S is defined as T acting on the stuff it acts on times S acting on the stuff it acts on. So
Yeah,
actually, no. So
that's exactly it. Yes.
yeah, wait, let me try to think of that again. So what you do is you define TS acting on a ton of stuff as T acting on like this part, and then
Oh my god, I think I figured it out.
S acting on, wait, what's like S acting on that part. Yeah. So with that in mind, can we do this? Yeah, I think we can. Okay, so with that in mind, how does this work?
Here, I think I got it. Maybe.
Mm-hmm.
So the whole point is that we're talking about what E1 F1 is. This is WI F1, which means it brings it to W1 times VI E1, which brings it to V1. So E1 F1 is W1 V1.
E1 F1 is W1 V1.
I don't even know, man. No. This is dumb. I don't get it.
Wait, can we start from scratch again? Just like make a new screen. I want to try like starting this from scratch.
Okay. Here, wait,
Okay.
but which point of scratch? Are we talking about this point of scratch? This is the actual point of scratch.
Like, okay. So we have a vector space V, and the basis is E1, which is equal to 1, 0, and F1, which is equal to 0, 1. Right? And then we have a vector space V star, whose basis is...
Whoa.
Oh, wait, hold on. Not F1. Sorry, E2. That would be E2. Yeah. Whose F1 is a map from...
You know what? Maybe instead of representing E1 and shit like that, let's represent it like this. Oh no, we literally can't. Fuck. The whole point is that the basis vectors you actually have to represent properly.
Yeah. And what was F1? It's a map from like... F1 is like you take in a vector. It was like you take in a vector x, y, and return the x, right?
Yeah.
And then F2.
Well, we'll pause. What we actually would have to do is that the basis implies a dual basis. But in this, this is the dual basis it implies.
Yeah, I'm just like writing down the dual basis. Yeah. So with that, now we have the tensor. the tensor v star. Yeah, v star, which acts on.
Here, I got something interesting. How about this? We say so this is a linear map. This is a, well, matrix, whatever that means, that takes in a W or takes in a covector, a vector, and returns
The covector acting on the vector,
which
is a
in
number.
my mind would be the equivalent of the identity. Am I right?
Yes, it would be, where you would have a vector here and a covector here.
Yes. And so in theory, this 1 should be equal to 1. Because that's what it is.
Oh, would it always?
Well, that's the point. It represents the matrix.
Wait, say that again. What 1 should equal to 1?
This year, when you decompose this abstract map into its components, assuming this basis, my intuition tells me this. Because of this.
Well, it wouldn't be 1. Wouldn't it be like the identity, like the like the letter?
But this is the component. This is the first component of the matrix.
Oh, well, there are 4 components, aren't there? Like
yeah. So then you have E21 is equal to 0.
Oh, okay.
E2 is equal to 0. This 2 is equal to 1. Like this.
Yeah, exactly. Okay,
match
yeah.
up.
That should be right. Yeah. Okay. That works.
But then what do we do? What do we do to confirm that?
I mean, that is true, I think. Let's just.
We have to confirm it.
Let's see.
This is something else that should be true. So matrix or linear map composition is equivalent to matrix multiplication in this way. So we should be able to arrive to that using, you know what? Yeah, like forget this thing. We should be able to arrive to this using only algebra of these things. Do you know what I mean?
I think so, but how do we do that? Like, how are we going to do this basis?
Okay, here, let's do it. We have 2 equations. These are our 2 equations.
Mm-hmm.
Let's do some algebra and figure out what these guys are.
Well, didn't we figure out that it was like 1, 0, 0, 1?
Well, that's like from intuition, but we should be able to do it with like actual algebraic perfection, just by manipulating symbols. So I think first thing we have to do is to translate this into WJFJ applied to VI EI.
VI EI, right?
You can pull the V out because this is just algebra.
Mm-hmm. It's just scalar. So WJV, and this is because of linearity, actually.
Mm-hmm.
And
And
then
then
you
these
have
two become the cancels out.
the F delta. Aha.
The delta implies that the two indexes become the same.
That is interesting. That is kind of cool.
So you get this is equal to VI.WI. If you expand that out, then you get it's equal to V1W1 plus V2W2, because they have the same index, right? And you're summing over I, that goes to 2. And then if you look at this here, okay, I see. Look, if you do E1 cross product F1, I don't know if you remember this, but we calculated this as being V1W1 from before.
Yeah, I think I remember that.
And then I bet that E2 F2 will become V2W1, which in this case it's 0, right? And then E2 F2 is going to become V2 whatever.
Wait, I'm kind of confused about this part actually.
So it's going to become 1, 1. When you match up the equations. Here, let's restart. Let's do a full restart. Let's do a full restart. So we have this.
Right.
Actually, so let's do this. Step number 1, we need to find out that E1 F1 is equal to this. We need to actually do algebra for that. We need to figure out what all of the basis combinations are, what all of these guys are.
Okay. So we would start with, so if we start with E1 F1.
Maybe we can even do it automatically and just do it over I. Maybe.
Not so sure.
But here, let's do 1, 1. But I bet there's a way of doing it where we keep it in the general case.
Wait, but like, how is this? Like, you need to have this acting on stuff.
Wait,
right?
Avnish, I think I have a good idea. Yes, you do have to act on something, but I have an even better idea. Look. So, okay, fuck it. Let's start with just 1, just as an example, okay? Let's say E1 cross F1, but we're doing this as an example, okay? Because later on, we actually want to expand this to find the general case. EI cross FJ applied to some abstract VW. Like I'm 100% sure we can apply it to the general case, but let's start off with a specific example, which we actually already did all the computation here, but let's do it again using just the algebra. So this would be applied to this.
Where W is like,
let's expand each of them.
So W is a covector?
Yes, but it can be expanded into WI, FI. This is our classic expansion, right?
Yes. And then the other one would be VI, EI, right? We're just expanding each vector into basis vectors. Cool.
We might have to use different indices though. Let's use J.
Okay. And then the way this is defined is
the way that the tensor product is defined.
Yeah. So the E1 acting on
So the W here, let's just keep it. Wait, first general. Let's expand later. Let's say WV like this. Just the general case first. And what is the general case? How is this defined? It's W E1 times F1V.
Right.
Now we can expand it.
Now we can expand. Okay.
Times F1 VJEJ. Okay, crucial point. E1 applied to Fi. What does it give?
You're summing over though. Like, hold on. E1. What?
We actually have Fi defined, I'm pretty sure. No, we don't. Fi is this.
Is it just E?
I'm pretty sure it's F1.
How?
Because this is going to be expanded, right? This is going to be F1, E1, F2, E1. Like just because of the way the sum works.
Yeah, so you're just gonna add these though, right? Well,
this is going to cancel out to 0.
F2, it is gonna cancel.
It's defined that way, right?
It is gonna cancel out to 0.
We defined it that way.
Right, because
Which
okay.
Which
leaves us with the
just F1.
Okay, what about the WI though?
Oh shit, no, does it? No, I think it just leaves us with 1. Because this cancels out to 1. Fuck. Wait, does it?
F1, E1, yeah, it becomes 1, right? Yeah, it does. It does. F1, E1 becomes 1.
No. Oh my god, but the I is the same I as here. So actually the full expansion becomes W1, F1, E1 plus W2, F2, E1. And this cancels out, which leaves us with W1, F1, E1.
Right,
This
but
cancels
F1,
out.
E1 becomes 1. So it's just W1.
W1 times.
Okay, now with that we have,
I mean, same story.
yeah, wait, let's write it out though. So F1 becomes, so this becomes,
You want to write it down?
yeah, so wait, if I just take this part, that'll become F1 times V1, E1 plus F2 times V2, E2.
Whoa.
No.
F1, E2, you're right.
Which means
You can always pull out the constant.
you can pull that out. So then, right, and then F1, E2 becomes 0, and then F1, E1 becomes 1 again. So you just have V1. So it's just W1 times V1.
Okay. So
Whoa.
E1 cross F1 is W1, V1.
Whoa.
But here, let's do general case here, okay? EI cross FJ applied to WV. General case. We're going to literally do the exact same math as here, but just general case. We get W applied to EI times FJ applied to V. This expands out to be.
There's no summation convention here.
What do you mean? Yeah, there is. Well, yeah, there is these two.
But they're not the same index. They have to be the same index for that to happen.
Oh.
Don't they?
Yeah, this is general case. You're right. So it is going to end up being like a matrix. Fuck. Wait.
It's kind of weird.
Let's just walk with it. See what happens. W. A.
Wait 1 second.
A. EI times FJ V B E B.
I don't know where this will work.
I
don't know if we can simplify this.
Well, this goes from 1 to, right?
I don't know. This is kind of weird though, because you can't be summing over the I's and J's. You're summing over only the A's and B's.
Well, we can still write it out. Let's actually sum over these guys. You get W1 F1 E1 W2 F. Oh no, EI.
Then W2 have 2 EI. But you can't do anything with this.
I actually think you can. Because EI is I is either going to be 1 or 2. Right? I is only ever going to be 1 or 2. And if it's a 1, then this guy gets canceled. And if it's 2, then this guy gets canceled. Like, do you see?
If it's a 1, then this guy gets canceled, right? Yeah. Okay. I do see. So you need to know what. Oh, so you need to like plug in
WIFIEI. I'm pretty sure.
Oh, that's true. That
Times
makes sense.
FJ, VJ, VJ. And then these guys cancel. These guys cancel. You're left with general case, VI. Boom. Holy shit, look at this. Is equal to. Isn't that so cool?
That is.
That means pick a 1 or a 2 here, and you get your formula. So E1 cross F1 is just W1 V1.
Right. E1.
E2 cross F1 is just W1 V2.
Oh, it's starting to make sense now. Yo.
And then finally, when you come back to here and you do the decomposition like this. So wait, first we actually have to do this. We have to say this is equal to WAFA VBEB. We did the math here. This one cancels out, I'm pretty sure, right? Like you get the delta.
I think so. I'm getting, it's hard to keep track.
Okay. This is our specific example, right? The one that is probably going to become 1001. We've got two equations. We're trying to merge them together somehow and to find the value of this. Oh, here. Okay, maybe we can actually do it nicely. Look at this. So we have this side and this side, right? We're going to apply both sides to a VW, right? Which in this case is just WV, because this is this doesn't actually simplify. This is our choice. Our choice, right? Of the map we're trying to decompose is this.
Like let phi equal this.
Yeah. And then you have this.
Ah, okay. Now we're getting somewhere.
Applied to this. This we freaking simplified.
Right. So that becomes
W, what was it again?
WIBJ.
Yeah.
Aha, and now we see the summation convention works.
Well, we actually need to simplify this or help this side out a bit. Or this one, we actually already did the work for this one. I don't know if you remember, but I swear it was VI or WIVI. Do you remember that or no?
I think I do. Yeah. Pretty sure I remember that, if I'm remembering the right thing.
The point is, if we write this down fully, we get 1, 1, V1, W1, plus 1, 2, V1. You see what I'm doing?
Yeah. And we should have some things cancel out.
And this one is written as W1 V1 plus W2 V2, which means this must be 0. This must be 0. This must be 1. This must be 1. Which is why we get a 1 1 1 0 0 1 when we arrange these ones in the order we like.
Oh, that's kind of.
Which is why this becomes this.
Oh yeah, that makes this is a big moment.
That's stupid.
Oh yeah, it feels like a lot.
Yeah,
like a lot of steps to get to something like this.
Yeah. Well, I think the highlights is that when you look at the tensor product E1, F1, it returns to you something unique. It returns to you these guys, which are unique. They're kind of like the bases themselves, you know?
Mm-hmm. That's crazy.
Okay. What do you think? That was a lot of thinking. Oh my God.
Yeah. I need to like redigest this again because like I don't know, like just after watching the lecture again, I thought I like got the tensor product, but like I need to like think this a little through even more.
Well, I think the most important part is being able to do this algebra of decomposition, you know? Like, you know how this entire time we've just been working with like replace the W with a WIFI and replace like just being able to do that and being able to do it quickly, and then you can arrive to conclusions like this probably much faster.
Yeah.
Like here, do you want to do the same thing but like speed round? And you do it.
I don't know. Like I feel like, do I get it enough?
Only one way to figure out, right? I'll be listening. I won't be like leading anything.
I'm not sure though. I don't know. I'm not sure like if I.
Maybe not. Yeah, maybe since we've already done it. I mean, we recorded this meeting, right? So you can always.
Yeah, I need to like rewatch this meeting as well. Okay, because like.
There's one other interesting property that I think is important. It's a bit weird though. It's the idea that the composition of linear maps is uniquely defined by the matrix product. Because when I'm writing down here is a bit weird. Basically, okay, so algebraically, if you did like a bunch of replacements, if you applied this to a VW and applied this to a VW, and then you did like a shit ton of simplification everywhere, you would find that they are equal. But the larger story here, like when you look at this equation, is that you can decompose a map like this into this, right? You can decompose this guy into this. You can decompose this guy into this, IJ, E1, F1. But the huge part is that you can do the multiplication of two matrices, two linear maps, by looking only at the multiplication of their matrices. Like it's uniquely defined. Crap, I don't think this is ringing for you. Is it?
I think it does, but it wasn't like, it only applies like when you're doing like, where like phi and psi are like 1-1 tensors, right? Like I sort of something like that.
Yes,
like
yes.
This is how you, like this is what leads to like the row times column thing.
Yes, right here. Yeah, row times column.
Exactly, but oh yeah.
But the point is, if you did, like, it's crazy, right?
But you need to do like a lot of, it takes like a lot of work to get from this to this.
Yes, but it's possible. And then the point is, you never need to deal with this again. You can do all of your math in this world, trusting that the composition of matrices is uniquely defined. It is equal, 100% equal to just what's happening with the components.
Yes, as long as you're aware that, as long as you like think that all of your as long as like you're working with matrices that are like this.
Of course, of course. But then you could come up with a similar proof for matrices that are 2, 1. But maybe it would be like the composition of those guys would be like something completely different.
Something different. Yeah. Oh.
Like it's just so cool. Like you can live in the component world and do everything in the component world without that it reflects the actual
reflects truth.
Vectors and tensors, which is why we are able to do all of our linear algebra like this. Like, look, this is literally composition.
Yeah.
Right. This is like psi. This is phi. And so beforehand, you had to like do this all manually and shit. But now you can just trust that the resulting matrix, the resulting IJ matrix, IJ, is going to be this.
Right. And then like,
because of the direction that it sums up in. Okay, anyways, that was a big brain destruction right there.
The tensor product like really is like at the heart of a lot of tensors, I feel.
Yeah. No, agreed.
Oh.
But it's cool.
Okay.
Like it's cool how you can represent anything using its components. Like it's cool how, okay, obviously level 1 shit is that you can do this, right?
Mm-hmm.
You can represent a vector by its components like this. But the craziest part is that you can do like your whole world in component land, including multiplication of matrices. Or if
Now, what I was like for the past like while, like what I've been like trying, like I feel like I'm on the verge of understanding in quantum computing why when you get like a system of 2 qubits, you like tensor product them. Like that's like, it feels like that's starting to make sense now.
Interesting. I'm not familiar with that problem, so can't.
It's like if you have, it's basically like if you have 1 qubit, you represent it as like a vector of 2 components. But if you have
cubic?
2
Doesn't the cubic have 3 degrees of freedom?
Qubit.
Oh, qubit. Oh my God, I heard cubic.
Yeah.
Qubit. Yes. Okay.
Yeah. So like that, but then when you have like another qubit, like C, D, and then you want to talk about them together, you do a tensor product.
Why?
that's what I thought the whole time. Like, why?
Whoa. Okay. Small issue. The tensor product is only defined for legit vectors and tensors. It's not defined for components, because this is a component, right? This would be like saying VI tensor product VJ.
Exactly. Yeah.
That's nonsense.
But in reality, like this,
I'm sure something's actually
is a vector.
happening here. Yeah.
And this is also a vector.
Or yeah, it represents a vector.
And then it's like,
why do you do that?
I feel like I was close to get, like, I feel like this is like helping get there.
Get that. Yeah. Finally understand that. Yeah. But I feel, like to me, I feel I've gotten to a point where like it sort of makes sense. And I feel the reason why is because I became familiar with this tensor algebra, I guess I'll call it. Like just like whenever I see a W now, I'm like, oh, try decomposing it. And oh my God, here you get a cancellation with a delta, right? Because you have like 2 bases. And that was like, I don't know, felt it helped me understand tensors more. Just the fact that I could like mess around with them. But yeah. Okay, anyways, do we have anything else to cover here in the tensor lecture?
The tensor lecture covers change of basis is a thing. It's kind of it's not that. Okay,
it actually is important. So, you know why? Okay, so you know this proof here? It actually does use change of basis. So that's like the one reason
to
learn it.
But like in reality, it's like, it's kind of like, Okay, I mean, wait, change of basis, like here is like about vectors. Where's the tensor stuff?
Oh, and there's also the whole discussion about
determinants. Determinants, I still don't like. Determinants are still kind of weird to me because I'm not like familiar with like regular determinants either.
Oh shit. Okay.
Like like I know like you kind of just do like
visually, you know what it does though, right? that it
It's
gives
like
you
it's
the
how much
area.
the area scales, which is interesting because in this lecture they said like to talk about determinants, you need to have volume defined.
Yes,
And
exactly.
then what you do, like I remember like there was one part where he had like a bunch of stuff over here. Oh yeah, okay. I'm sort of remembering. It was like this is like a volume thing, and then like you have
Yes.
that here, and this makes sense because it's like this is the new volume, this is the old volume, and then you're
Yeah.
dividing to see how much the volume scales.
Well,
Like
no,
that.
that's exactly it was exactly this. So you had this is something called a top form, which is exactly as you mentioned. It's a tensor of the top amount of vectors that it takes. Like it takes like a bunch of vectors and returns a number. And if you think about it, this is just the definition of the volume of a function that measures the volume, right? It takes in a bunch of vectors and it returns a number.
That's true. Wait, that makes sense because you just multiply the vectors.
And because it has to be multilinear, the visualization is that it's gotta like give the actual volume in some sense. Like
yeah, so like you multiply this by this, and then
yes, it has to give you an actual number. So yeah, and so that's what it forcefully happens. Eventually, you'd say the determinant of this linear map is equal to the top form applied. The top form applied.
And it's applied to any arbitrary. I think it was like any arbitrary thing, right? Or it was something like that.
Yeah.
Or maybe not.
It was something like this. I'm obviously using the wrong symbols here, but the point is that you take the volume applied with the linear map on the top, and then you divide it with the volume just applied to the. Oh, it's the basis. It's the basis. That's
what that makes sense.
Yeah. So that's literally just what it like. It makes so much sense. Of course,
that all like suddenly clicked now. Hold on. Yeah, because like phi is like the transformation.
Yeah.
Right. Like how the basis vectors transform.
And so it might shrink the space or well, whatever the.
Yeah, like this is just the volume spanned by the basis vectors. And then that's just the volume spanned by the new basis.
Because it's kind of cool because the volume that you get returned from here is kind of arbitrary. That's true. Like it could be like a billion times the thing.
Yeah, but it's like how much it scales that we're interested in.
Cool.
This is cool stuff.
Determinant makes sense.
Yeah.
This is so shocking though, because this is so obvious to me. Like of course if the determinant is defined as the scale in area, it's going to be defined as the area originally divided by the area.
What I don't know though is why this is the determinant of this is equal to AD minus BC. Like that's
I will give you a bet that if you were to choose a top form and then you were to do this algebra here,
it would work out.
Algebra, it would work out. I guarantee it that the algebra would work out somehow to give you like, wait, what would this even be? This would give you fucking this. So it would tell you the determinant of this is equal to, what is this? AD BC? What is that? AD is going to be down the diagonal.
This kind of makes sense, right? Because like these E's would probably be like 1, 0, and 0, 1, right? And then the volume would just be the same thing.
I'm sure if you did the algebra, it would work out into giving you like exactly this. It would give you this. It would give you this 1, 1. This D is 2, 2 minus this 2, 1, this 1, 2. That's what it would give you.
Yeah.
I mean, because that's what it actually is, right? When you give it.
Yeah.
So I mean, I would do that now. Obviously the meeting's like kind of too long though. So
yeah, but it's
this would solidify my understanding of tensors to 10 out of 10 if I actually like did it in its components and figured it out. But yeah, this meeting's been like too long, so I'm not sure if you're like burnt out.
Yeah, I'm kind of like I need to like process stuff. I think like the craziest thing though is like how, like the world you live in like high school and undergrad in math is like it's like a very specific case of the general Like it's crazy.
It bothers me, yeah. Like
the row and column vectors, and they're always like 2D or 3D. Like this is
yeah,
just such a
they're
specific
arranged in
case.
a special way, and then determinants is defined as like this weird thing, bro.
Just such a special case of like insanity of like vectors and homomorphisms and like friggin' tensors.
Yeah. It's crazy, yeah.
And
like,
tensors are like
even this here is a special case of linear maps from V to W. Think about that. Where this over here is the equivalent V.
And tensors are kind of like the all-encompassing, like the highest level of vectorness.
Yeah, to some degree. Yeah, like abstracts over. It's weird. I don't know.
Like if you think about like a matrix is a vector, right?
I don't know about matrix. A matrix is a made-up thing. A linear map, a linear
map, yeah, because we use like in high school, like what we call a matrix is just a linear map. A linear map from V to V.
Okay, this is weird. So it's kind of like it represents a linear map. It uniquely represents, because it's kind of like saying, like I'm sure you've heard that a function f is just a subset of a cross b, the power set of a cross b. I'm not sure if you've heard it. So yeah, a function is just
exactly
equals, but it is uniquely represented by this weird formulation here. This makes no sense as like what it actually means, but it uniquely represents it, right?
Yeah, it's just a subset of all of the possible tuples. It just so happens that all of those tuples behave in such a way that the second entry of the tuple is the square of the first entry.
Yeah, so in this case, it would be f of x. Yeah. No, it'd be x.
Like we're used to thinking of like f of x, when in reality, like f is the set of x, y pairs.
No, well, it's the set of x, f of
obey
x,
something.
Like this.
Yeah, oh. Yeah.
Okay. So the point is, like this uniquely represents what actually happens. And the same thing happens with a matrix, where the matrix uniquely represents what is actually happening with the endomorphism here.
That's cool.
Which in this case, as we did literally just now, is this. It applies the covector to the vector without doing anything.
Bro, like I swear the past like couple months.
Oh my God, look, that's literally what it does. You have like A, B, you have
C, exactly.
That's literally, it literally just applies this to this. It literally just like disappears. So cool. Okay.
It's like the last few, like this is like totally changed my perspective on math. Like these like lectures, like this whole thing, like totally changed my perspective on math.
It's actually taught properly. Oof. So
like you see things differently. Like it's crazy. Like you think of like, this kind of thing as a thing, and this is like a different thing. And like then you have matrices, which are their own thing, but like they're all part of something.
Yeah, that's so cool.